Hey guys, this is Joseph from startdataengineering.com. In this tutorial, we're going to see what change data capture is. Using a simple example, we are going to be using Debezium, Kafka, and Postgres for this tutorial. This tutorial is available at startdataengineering.com in blog format. So if you'd like to follow it there, I will leave a link in the description below. Let's get started. So the first thing is, what is change data capture? So change data capture is a software design pattern where a change in a source system must be captured in a destination system. So you can think of it as having an app which writes to a database and a system that captures these writes, which may be read, update, or delete, into another system. There are reasons why we want to decouple those two. The main reason usually is that we don't want to impact the performance of our application. There are other use cases are moving data to an Elasticsearch index to keep Elasticsearch cluster up to date with the available data, or transferring data from a OLTP system into an OLAP system. So in this use case, you might have to do some transformation, and you don't want to be affecting the source system. So these are some of the use cases where you will want to use a change data capture software pattern. Okay, so let's get started with our example. So our problem is that, let's assume we have a application that does a simple CRUD operation on a holding table, which has the type of stock you're holding and the quantity of stock you're holding, and a user ID and holding ID to identify the holding and the user who owns that holding. But we want to be able to answer questions like how many times a specific user changed the stock type or stock quantity, or what is the commonly sold stock among all users in a given date range. Usually when you want to answer questions like this, it is sometimes difficult to answer them directly on your OLTP table because you're not really keeping a log, you're just keeping the state of your system. So what people generally do is they convert this OLTP type table into an OLAP type table to keep the log of changes. Usually this is done using a key value structure. So if you look at this diagram, you can see how we are transforming our OLTP structure into an OLAP structure. So the OLAP table, called here as holding pivot, is going to be an append-only log. So whenever a user makes any type of changes like create, update, or delete, it's recorded in the OLAP table. So now you have a running log of everything that is happening in your OLTP database. Using this, you can actually answer complex questions that involve time ranges, and you are essentially keeping a snapshot of your state, of your OLTP state, using the holding pivot or OLAP table. If you're interested, you can take a look at the query in the blog. Again, I'll add the link to the description below. So let's look at the design. So this is a basic overview of what we are going to do. We're going to keep a Postgres database, and we're going to assume that is our OLTP database. We are going to use Debezium with Kafka to record changes from our Postgres database, push it into a Kafka message, and we are going to have a consumer application read from the Kafka message and output it to a text file, which is the OLAP structure that we want. So this is a follow-along tutorial. So I recommend you install Docker and PG-CLI to follow along. Docker is very convenient because you can easily spin up different tools or different systems easily. And in this tutorial, we're going to use Docker to run Postgres, Debezium, and Kafka. PG-CLI is a command line interface to connect to our Postgres instance. So this is the Postgres Docker container command. So a little bit of information here. So we want to understand what actually happens when you write a transaction to the Postgres database. So when a transaction comes in, let's assume a read or update or delete comes in, what Postgres database engine actually does is it records the transaction in the cache, but writes a log to the transaction log called write ahead log in the disk. The reason it keeps all the data changes in the cache is because it wants to reduce the overhead of writing to a disk. So in this scenario, it only writes once to the write ahead log, and the rest is kept in the cache, and periodically it's flushed out to the disk. The reason for this pattern is because they wanted to reduce the latency of Postgres, but also have a log in case the system crashes and you want to recover from the disk. So let's go ahead and start this Postgres container. Oh, I think I have been running all my Docker containers. I need to stop them first. Let me stop them. So let's take a look at this Docker container. We are starting a Docker container. D flag stands for detached, meaning run in the background. Name for our Docker container. Port, we are opening port 5432 in our local machine to 5432 inside the Docker container. So you can access Docker container using 5432 port, creating a user, creating password, just password, and we are actually using Debezium's Postgres version. The reason for this is that we need to make some changes, configuration changes to Postgres. So Debezium Postgres already has that made, so it makes it easier for us. So let's start that. Let's take a look at these configuration changes that we need to set if we were not running Debezium's Postgres version. So let's see. So docker exec-it basically lets us execute commands in the Docker container in an interactive mode. Let's bash into it. Oh, my bad. It's actually Postgres because that's the name of the container. All right, so now we are inside the Postgres container. So this is where the configuration file is. All right. So let's look at these. This is the main thing. So write ahead log level. So this controls the amount of information written to the transaction log. Usually it's set at minimal because that's all the database needs to recover in case of a crash. But we are going to set it to logical because it records a lot more data that our consumer can use. And maximum write ahead log senders, these represent the maximum number of processes that Postgres can run to send these write ahead logs information to the consumer. And that's that. Okay, so let's log into our Postgres instance and create some tables. So log in there, password is password. So if you look at this, we are creating a schema, setting our search path to our schema, and then creating a table. Let's just copy that over. All right, this is an interesting command. So we're saying alter table bank holding replica identity full. So replica identity controls the type of information that's written to the write ahead log. So what that means is if you set replica identity to full, it will record the before value and the after value. In case of an update, you'll have the before value available and after value available. Without setting replica identity to full, you will not have the before value available. We will actually see the exact structure in one of the later sections. Let's also insert a simple record into bank holdings table, and let's quit that. So just to recap, we have started Postgres. The next part is starting Kafka. So a quick introduction of Kafka. Kafka is a distributed system which lets you create and manage multiple queues. People usually call Kafka as Kafka broker, which denotes the system, and it can have multiple queues. So a topic is what a queue is called, and a producer or consumer can either write to a specific topic or read from a specific topic. And partitions are basically the way to distribute the topic amongst the cluster. So if a topic is too big, it's generally distributed among different machines in the cluster. And each partition has something called a offset. An offset is a pointer that points to the message that you are currently reading from the consumer. So this goes to offset setting either in Kafka or consumer. We are not going to go into that in this scenario, but remember that if you are reading messages from a Kafka topic, you need to be aware of where your offset is, or have logic in a consumer that behaves the way you want to. In order to run Kafka, we also need Zookeeper. Zookeeper is a cluster management system that Kafka works with in order to manage resources of the cluster. So let's go ahead and start Zookeeper. So you'll notice that we are opening up certain ports from Zookeeper. These are all ports that are required by other systems to interact with Zookeeper. So we started a Zookeeper container and a Kafka container. And from Kafka, we have opened up port 9092 for, again, other systems to communicate with Kafka. Okay, so this is the Debezium part. So right now we have a Postgres setup, we have Kafka setup, and now we need to start Debezium to read data from the write-ahead logs in Postgres and push it into Kafka queues, or topics to be specific. So let's start connect server. So Kafka actually has a tool within its ecosystem called Connect, which is an easy way to integrate your services to Kafka cluster. So you can use a connector to read in data from other data sources to be pushed into a Kafka message queue, and vice versa. You could actually also use a connector to read data from Kafka topics into an sync system. In this scenario, we are starting a simple Kafka Connect container. So let's take a look at the specifications. Again, opening up port 8083, we are creating a link to Kafka, the container that was created before. We are creating a link to Postgres because this Connect service needs to be able to read from the write-ahead logs in Postgres. Bootstrap servers, asking the Connect service to use Kafka as its server. Group ID. So group ID is a logical unit within a Kafka ecosystem. So we are just calling it SDE group. Config storage topic, offset storage topic. So config storage topic is a topic within the Kafka cluster which stores your configuration, and similarly offset, it is again a topic within the Kafka cluster that stores your offset information for your specific service. So as mentioned earlier, offset is a pointer pointing to the message that has been recently read by the consumer. So we can communicate. So now that we have a Connect service up, we actually need to start the Debezium service in that connector, in that Connect service. So let's first see if we have any other connectors running. As you see, we have nothing running. So we can start Debezium connector using a curl command. So it started. So let's take a look at this Docker command we are using, and specifically the -d flag. So this specifies the configuration for our Debezium service. So we give it a name. We're just calling it SDE connector. configuration. We are setting a Postgres connector because our database is Postgres, and we are setting our database specific information here, setting the host name, port, user, password, DB name, server name. So server name is the name we assign to the server. For now, we are just calling it bank server 1. An important thing to notice here is this table whitelist, bank.holding. So by default, Debezium reads excuse me, all the tables in your schema, but we can specify specific tables or specific schema using whitelist, and you can also use backlist to ignore specific schemas or tables. So if we check the list of connectors using the skull command, we'll see our HDE connector has been registered. So now we have the Postgres running, we have a Kafka cluster running, and we have Debezium connect service that is reading data from Postgres and pushing messages to Kafka. The next step is to to launch a consumer to see the messages that are in the Kafka queue. So let's run this. Let's clear this. So this docker run command starts a Docker container called consumer, links to zookeeper, links to Kafka, and this is the Docker image. And we say watch topic, and we assign the topic name, which is basically this bank server name dot our database name, which is bank, and our table name, which is holding. And we say max message is 1, which means it'll only read the first message and it'll stop the Docker container. So let's take a look at it. Let's see. Yeah. We have to write this. Do that. So it's reading from the Kafka messaging queue, and it stopped after processing one message. So this is your message. These are just some print statements from your container. This is the message that we want. This is really hard to read, so what you generally do is you can read the message and pipe the output to a grep just to ignore the non-message print statements, and you pass to a tool called JQ, which is a lightweight JSON parser. It's reading the first message in the queue. There you go. So you can see this huge message. This is just one message. So let's understand what this is. So when you take a look at this huge JSON, you can see two main parts. One is schema. The other one is payload. So schema is basically a JSON object which contains the structure of your payload. This is because some source systems can use this structure to parse the payload. So if you take a look at the payload, you will see the before section, the after section, the source section, and operation type, the transaction millisecond, transaction time, and other configurations for source like version, connector name, when this transaction happened, snapshot, database schema, table, transaction ID, log sequence number, etc. So we initially created the first record a while ago in the Postgres section, which was 1 VFIAX 10 that has been recorded as after. and it's showing up as read because Debezium tries to catch up with the available data in your write-ahead log. So since we have already created it, now Debezium is actually reading it, and hence it's showing up as read. So now that we have our payload and schema, it's time to actually parse the JSON output using a Python parser. You can actually go through this file, but basically the idea is take every incoming line as an input, and depending on the type of operation, if it's create, read, or update, parse it out to the corresponding fields. So it will match the holding pivot table structure we have defined in an earlier section. So let's try running this. I'm gonna copy this Python file into my local system. Okay, let me just check if I pasted it properly. Yep. So if you notice here at the top, you might notice we have a underscore dash u. The dash u flag denotes unbuffered. Because we are going to be running Python in a streaming fashion, we wanted to take an input and just print out the output. By default, all Unix, when you pipe multiple Unix commands, it has a buffer. The size depends on your operating system, but in this case we are saying do not buffer it, just take in an input, process it, print it out. Right, so let's use this docker command to start our consumer, and we are going to pipe the output of the consumer into the streaming Python script that we just created, and the output from that will be written to a file called holding pivot.txt. So what this command did was it started a Docker container called consumer, which watches the topic bankserver1.bank.holding and removes unnecessary lines and passes those to stream.py, which is our Python script we saw earlier, and the output of the Python script is going to be stored in data holding pivot.txt. So let's open another terminal to follow data holding pivot.txt. So if you're using multiple terminals, I have to be in this. If you're using multiple terminals, it's convenient to use this tool called tmux, which provides you with multiple screens and easy navigation between them. Let's follow so nothing has been written so far, but let's see what happens when we make a change to the table. Let's log into our Postgres table. Password is password. Let's try an insert statement, which is a create. So what happened here was this insert statement was written to our write-ahead logs in Postgres, which was read by Debezium and pushed as message into our Kafka cluster. And this consumer reads from that topic, parses it, uses our custom Python parser, and writes to the file. And this is the data written to the file. So if you take a look at this, you'll see before it was none and it became S&P 500 in the after column. Same with stock, none to 1. That's because this value did not exist before. So it makes sense for it to have none as the before value. Let's try another insert. Again, same. You'll see it went from none to SP 500. Let's see what happens when we do an update. So we are updating the holding quantity, where holding ID is 1000. So this is a little bit tricky. If you look at the holding stock, the before and after value remains the same. That is because we are not updating holding stock. We are only updating holding quantity from the previous value 10 to current value 100. I think this 10 was remnant from a previous test I was running, but you get the idea. It's changing from previous to current. So let's see what happens when we delete. You would assume it goes from a certain value to none. So you have to press yes. So as we assume, it went from S&P 500 to none, similarly 1 to none. Same thing when we delete user ID 2. That's because we didn't have... Sorry, it went from S&P 500 to none and 1 to none for user ID 2. You can insert some value. You can play around with it to understand it better, but that's basically the idea. Any changes you make to your table is read by Debezium, pushed into Kafka topics, which can be read by consumer, and you can parse it however you want. In this simple example, we are just pivoting it into a different format. Let's look at the data flow once again. Postgres writes the write-ahead log, which is read by Debezium, pushed to a Kafka topic, which is read by your consumer, and written to a text file. And these are the commands to stop all your running Docker containers. So let's just stop everything. There we go. We stopped all our containers. So that's a quick overview of what change data capture is. And some of the things to be aware of if you are thinking about implementing change data capture is that in this scenario, we were capturing only the data changes, not data schema changes. DDL type changes can be tricky to capture and use. And you also need a Postgres version 9.4 or higher. And when you set your write-ahead log configurations, make sure that you're not overloading the database. Although write-ahead log is supposed to be or designed to not impact database performance, setting some of the write-ahead log store data size or number of write-ahead log processes too high will definitely impact your database performance, so be aware of that. And this is a distributed system. There are multiple points of failure. For example, your database could crash, and then Kafka cluster could crash, and your consumer may error out. So in case of all these errors, always have a backup and recovery plans. Like, what would happen if your consumer crashed? Will it automatically restart? If it restarts, will it read the messages it read before, or will it skip the messages it read before? So you have to think about all these things while you're designing any distributed system. And the last thing to be aware of is Kafka and Debezium, they offer at least one event guarantee. So what this means is any change event will definitely be delivered at least once. But that also means it can be delivered more than one time. In certain cases, this might be okay, but depending on your consumer logic, it might cause data duplication. So be aware of that. A common pattern people use in consumer systems is upsert, which is update or insert. Update if a primary key value is already present in the source system, in the sync system, or insert if the primary key value is not already present in the sync system. So that's it for this change data capture tutorial. Hope this gave you an idea of what change data capture is, how to use it, and things to be aware of if you're thinking about using it. And if you have any questions, leave leave them in the comment section below. I'll try to answer them all. Thank you.